Now that we have covered single-phase power, we can better understand why three-phase is the norm. Returning to the concept of instantaneous power is the product of voltage and current with respect to time. Single-phase circuits, therefore, with alternating voltages and currents, produce instantaneous power that oscillates at twice the system frequency. Assume that the current and voltage waveforms are overlaid. Three-phase circuits, by contrast, produce a constant instantaneous power output, which is preferable. Also, when compared to single-phase circuits, the peak currents are lower for the same power flow in three-phase, requiring less material and making three-phase more economical from an infrastructure perspective. Interestingly, while higher-order phase systems can also provide constant instantaneous power, there is no benefit to having more than 3 lines for power transmission. This leads us directly onto our next topic, three-phase sources. Three-phase synchronous generators output 3 discrete waveforms that can be considered as 3 independent voltage sources. While being equal in magnitude and frequency, they are each offset from each other by 120 degrees. This ensures that they are evenly spaced through 360 degrees of rotation, that is, a full cycle. First A, then B, then C, at regular intervals. Here are the current and voltage values of each phase in phasor form. Note, the current is lagging the voltage by some amount. Also note the 120 degrees shift from one to the next. Here they are represented graphically. Note again the offset. As the voltage vectors all have the same magnitude and are offset at 120 degrees, they sum to 0. The same applies for the current vectors. When the magnitudes and phase shifts are regular like this, the source is said to be balanced. Formally, in a balanced three-phase system, we have the voltage from A to neutral, plus the voltage from B to neutral, plus the voltage of C to neutral is equal to 0. Voltage sources are typically connected in one of 2 main ways: star, also known as Y, or delta. Beginning with star connections, we can begin by defining some of the characteristics of a star-connected source. The most important feature is this common point, called the start point. When a return wire is connected, it is also termed the neutral. When observing sources, it's important to note that there are 2 different ways of looking at current and 2 different ways of looking at voltage. These are phase current and line current, as well as phase voltage and line-to-line voltage. A phase current is the current that passes through any one of the 3 phases. A line current is the current that exists on the line. A phase voltage is the voltage across any one of the 3 sources. And a line voltage is the voltage that exists across any pair of lines, for example, VAB. In the specific case of star-connected sources, it can be seen that the phase current, that is the current through one of the phases, is equal to the line current as they are all connected in series. However, the phase voltage does not equal the line-to-line/line voltage. However, with the creation of a loop, we can see, using KVL, VAB is equal to VAN minus VBN. This in turn is equal to Vm to the angle of 0 degrees minus Vm to the angle of negative 120 degrees. Using vector arithmetic, we can see that the answer is root 3 Vm 30 degrees. What we find is that the line voltage is a scalar root 3 larger than the phase voltage, while also leading the phase voltage by 30 degrees. Now continuing with the second type of connections, delta connections. Here is an example of a sample circuit. Using the framework of classes we talked about with star connections, we can now see some reversals. Where previously the phase current and line current were identical, in this situation it's easy to see that that is no longer the case. Take for example this point, where in a star connector it was only one phase current moving into that node. Now we can see that there are in fact two phase currents influencing the line current. That said, when it comes to voltage, in delta connections, the phase voltage and the line voltage are the same. This is readily apparent when you see that VAB is positioned between IA and IB. So the phase voltage across this phase will be the same as the voltage drop from IA to IB. Moving back to the current situation, we can perform similar analysis, this time using KCL. At that top node, the sum of the currents moving in and out must equal 0. Therefore, IA moving out plus ICA also moving out minus IAB moving in is equal to 0. Rearranging, IA is equal to IAB minus ICA. Using vector arithmetic, the phase current in line A is equivalent to the line current across AB multiplied by root 3, lagging by 30 degrees. This same result can be found at the right node and at the left node. We can see here that the line currents are root 3 times the phase currents and also lag the phase currents by 30 degrees. We've seen two different types of connections. Now we will figure out how to transform between them. This is necessary because we like to work with star loads as they give us ready access to line currents. For this to be possible, the line voltages must be the same, meaning if you are looking from the load, you would see the same thing if it was star or delta. Expanding this equation, rearranging, therefore, a delta source can be replaced with a star source with the phase to neutral voltage given by this. A good thing to remember is that if you are given a voltage on a piece of equipment, it will always refer to the line voltage, that is, RMS line. Three-phase balanced loads operate very similarly to sources in both star and delta. However, this time it's the phase impedances that are equal in magnitude and in phase. For star loads, here are the voltage and current values. In summary, the line voltage is different to the phase voltage, but the line current is the same as the phase current. For delta loads, here are the values of the current and voltage. In summary, the line current is different to the phase current, but the line voltage is the same as the phase voltage. So how do we convert impedances between these different system configurations? Luckily, there is a basic equivalence between star and delta. This takes the form of the impedance in the star network being equal to the impedance in the delta network divided by 3. This means that a delta connected load with 3 times the per phase impedance of a star connected load would, when connected to the exact same source as that star connected load, display the exact same current values on each line. We will now analyze a balanced star-star three-phase system. This is because almost any other system can be converted to this type, which means that familiarity with its structure will be very useful. You can see here a balanced source in star with a neutral, and a balanced load in star, also with a neutral. You'll see as well 3 identical line impedances. An important feature in balanced star-star three-phase systems is that the current in one neutral is equal to the current in the other neutral, which is equal to 0. That is, if the load impedances are equal, then the current in the neutral on both sides is 0. We can prove this mathematically. Firstly, we know that the load is balanced. This means that each of the 3 impedances are equivalent and equating to some zy. Taking into account that each load impedance is in series with a line impedance, we can find the total impedance per phase. Now we perform KCL at one of the neutral points, say here. We know that the sum of the currents moving into or out of a node must equate to 0. Therefore, further, if we take the KVL at each phase, we can find another representation for the current in each phase. We can now replace the line currents in this equation by their expounded alternatives. Knowing the generalized impedance per phase, we can further rearrange this. Finally, we can readily infer that the line currents add up to 0. Thus, the current at the neutral point is equal to 0. It can be clearly seen how this applies to the other neutral as well. This means that in a balanced system, if the current in the neutral is 0, a neutral wire is unnecessary. Because the current at this point and at this point is identical, it's not necessary to join them. This is the reason why high voltage transmission systems use only 3 conductors. Also, take note that if these 2 neutrals were connected and there was some sort of impedance in between, the voltage drop across this impedance would be 0. This is an important result as it allows us to look at this balanced 3-phase circuit as 3 independent single-phase circuits. This means that we can use per-phase analysis. These phases can essentially be decoupled, allowing us to analyze a single-phase circuit and then extrapolate the results. Here we have one of the 3 phases. We can now run calculations on this phase and then extrapolate the results to the other 2, as the only difference will be a small phase shift. In summary, convert all delta loads and sources to equivalent star connections. Remember, all neutrals are the same potential. Solve phase A alone, then the other 2 can be observed. If needed, return to the original circuit and determine line values or internal delta values. This concludes the session on AC systems. If you would like additional information, please consult the lecture notes and recordings. To conclude, we are going to run through a simple exercise involving balanced three-phase systems to reinforce some concepts. A balanced three-phase 208 volt source supplies a balanced three-phase load. If the line current IA is measured to be 10 amps and is in phase with the line-to-line voltage VBC, find the per-phase load impedance if the load is A, star connected, B, delta connected. We're going to have to convert between line and phase quantities in this question, so I'll put some helpful formulas in the top right corner. Knowing Ohm's law, to find the per-phase load impedances, we must divide some voltage by some current. For the star-connected load, we'll need a phase voltage and a line current. For the delta-connected load, we'll need a line voltage and a phase current. Let's write them out over here. As we know, this quoted voltage magnitude will always be in line voltage. So if we want a phase voltage, we must divide the magnitude by √3. Because this is our reference voltage, we set the angle to 0. To find our line voltage, we already have the magnitude, and we know from our formulas that it will lead the phase voltage by 30 degrees. For the line current, again, we know the quoted current magnitude will always be in line current. To find the phase angle, we have to complete an intermediary step of determining the phase angle of VBC. Luckily, we know that all phases are offset by 120 degrees. We also know that VBC will lag VAB. Therefore, if our VAB is 208 at an angle of 30 degrees, we know that our VBC will be 208 at an angle of negative 90 degrees. Therefore, because it is in phase with the line-to-line voltage VBC, we know that our angle IA is going to equal negative 90 degrees. Lastly, for our phase current, we know that phase currents, according to our formula, are just line currents divided by √3, leading by 30 degrees. Inputting our value for our line current, now that we have all our parameters, we can plug them into our formula to find the per-phase load impedances. For the star-connected load, this is the phase voltage divided by the line current. Plugging into our calculator, we get 12.01 ohms at 90 degrees. For the delta-connected load, this is the line voltage divided by the phase current. Plugging into our calculator, we get 36.02 ohms at 90 degrees. Finally, we can check that we've done our mathematics correctly by recalling that when converting between a star and a delta load, you multiply by 3. And there we go. We've confirmed that we have the correct answer.